want to design 4-bit AU. So what is the AU means? AU means arithmetic unit. So arithmetic unit is the unit usually you have inside the CPU, and that unit is responsible for doing any arithmetic calculation, right? This is actually a very simple one, but we have another unit inside the CPU. We call that logic unit. So whenever you want to do any logic operation, you use that unit. So one example for logic operation is the all, and, or, not. They are actually logic operation, right? So that means you have the arithmetic unit, you have the logic unit. So then you actually combine these two, you make RLU unit. The RLU actually is the arithmetic logic unit. That's the unit that's able to do the arithmetic operations and also the logic operation. So we start with very simple arithmetic unit, 4-bit arithmetic unit. So if we actually go to more detail about these arithmetic units, so I actually put the table here, which is summarize how these arithmetic units should work. So see, we actually have two address bar. We call that A0 and A1. So we keep actually one column, we call that operation. And here you actually put another column which shows you what exactly should be the job of that specific case. So you have two input, A0 and A1. So definitely you could make 4 different bit pattern. I summarize them here. So in this unit, whenever you give A0 and A1 0, 0, it should actually do the add. What it means, add means you actually add the number X, which is 4-bit, with number Y, which is 4-bit, and if you have the carry, it's able to actually add with the carry too. So whenever A1 is 0, A0 is 1, what the unit should do is increment. So what it means the X that you have, which is the number with 4-bit, increment that by 1. So that means it should be able to calculate X plus 1. So whenever that is 1, 0, so it should be subtract. So subtract, subtraction means it should be subtract X minus Y. And whenever you have 1, 1, it should be actually the decrement, right? It should be give us X minus 1, okay? So X minus 1, okay. So that means this is what I call the arithmetic unit. I want to design a unit, definitely is 4-bit unit. So I actually have 2 bits, which is I could tell that unit what you need to do. So could you tell me how many inputs we have in this unit? Just type that on the chat box. Guess how many inputs we need. So maybe I need to summarize the unit here. You help me how many inputs and how many outputs we need. So I call this AU. So the first question is how many inputs we need. Guess 2, 4, that's right. How about this Cin? Because whenever that's 0, 0, we need to actually have one input carry, right? So we need 1 for that too, right? So that means you are right. 1, 2, 3, 4 X, 1, 2, 3, 4, 4 Y. But because for this case you need to add with carry in, so that means you need to have some C, right? That's right. So how many outputs we need for this unit? And another things I forget, so we need more actually input. X, Y, scene. How about this? We need actually two address, which is tell us what the unit should do, right? So this is input. So I need A1 and I need A0, right? So which is depend on what I put here, it's actually do X plus Y, X minus Y, X plus 1, or X minus 1, right? So how many outputs I need here? So definitely all of them is input, right? How many outputs we need? So because we already designed the 4-bit adder, 4-bit subtractor, you should be actually able to answer that question. How many output we need? So if this is just adder, that means X plus Y 4. So see, if it's for the, just review the whole function of this unit. First, it's should be able to add these two numbers plus C in. This is 4-bit, this is 4-bit. You could have one here. If you add two 4-bit numbers, what should be the answer? All the time is 4-bit, or it is possible you get 5-bit. Yeah, definitely 5. So that means the answer is this. Definitely you need 4. You need one C if I call this S0, S1, S2, S3. Definitely you need the carry 1 because why? Because whenever you add X plus Y, which is both 4-bit, probably you get 5-bit. So that's the reason you need to see C4. What other outputs you need? So this is for this. Whenever I comes to the next increment function X plus 1, if you get the carry, definitely you already have. So nothing more you need for the second functionality. How about X minus Y? If this unit able to subtract two numbers, what other outputs I need? Is it possible the numbers get the negative whenever you subtract two numbers? Yes or no? So definitely whenever you say X minus Y, definitely you could get negative. We talk about this in subtraction, right? 4-bit subtraction. Check that video, how you could make the 4-bit subtractor from 4-bit adder. So X minus Y, definitely you need a sign. So because maybe you actually get the negative answer, so I need to have one output, which is keep that sign, and X minus 1 is actually the same thing, right? So that means if it's negative, you're able to keep this here. And definitely whenever it is subtraction, you never get the carry, right? You just have number here, and it is positive or negative, you could keep here, okay? So this is actually the whole story. I want to make a unit which is depend on what I give here, do these 4 functionality for me, which is add two numbers, subtract two numbers, increment by 1 or decrement by 1. So this is what we want to design. So again, the only tools that we have here is the 4-bit adder, okay? So that means the only things that I have here is 4-bit adder. So that means if I back here, yeah, this is the only tools that I have. So I have just one 4-bit adder. So this is 4-bit adder. So this is the only tools that I have. Yeah, probably I need to expand that because we have too many. We will have too many things here. So consider this. This is the only things that we have. Okay. So definitely whenever you have 4-bit adder, you know what should be the input and outputs, right? The 4-bit adder has how many inputs? 4-bit adder, we actually talk about the 4-bit adder. We have a video for that. So 4-bit adder is able to add 4 numbers, right? 4 2-bit numbers. You could have the carry and give you the output, okay? So I just draw the inputs. So you have 4 inputs. 1, 2, 3, 4 for X. So you have another 4 for Y. So this is 1. This is 2. This is 3. This is 4. And you also have 1 carry here. Okay. Cn. So this is Y, this is X. How many outputs we have? We have actually 4, which is 1, 2, 3, 4. Definitely you have 1, actually the carry in your 4-bit adder. We already talked about the 4-bit adder. So review what we want to do. We have just one 4-bit adder, which is able to add 2 4 numbers. This is X, this is Y, and the carry input carry. It's able to give that number in 4S output, and also if you have a carry, it puts here. So, but what we want to do, we want to design a arithmetic unit which able to do these 4 different function. That means whenever we give a0, a1, it's able to add x plus y plus the carry. Whenever this is 0, 1, it's give us x plus 1. Whenever this is 1, 0, it's give us x minus 1. Whenever that's 1, 1, it's give us x minus 1. Okay, so back to this here and see if I check this. Whenever you want to, if you check the whole these columns that you have, you could guess what we should give in these 4 inputs of these 4-bit adder based off these 4 functions that you need to do. So that means all the time, no matter what you have in AC, A0 and A1, what will be happen? The first number all the time is X, right? Here is X, here is X, here is X, here is X, right? So do you agree I put x0 here, x1 here, x2 here, x3 here? Why? Because no matter what you have in the address bar, all the time the first number should be actually x. Here should be plus this. Here again, this is x, should be add with this. These are the subtractor, but we already know you could actually use the first complement and get the subtraction by actually add that with the first complement of the second number. So that means for this, we are doing x plus the first complement of the y. For this, we are doing x plus the first complement of this. So that means definitely in all of them, we have x plus something, right? So that means no dot these first input of these 4-bit adder, we should actually put the x, okay? So how about these 4 other input that we put the y here? So I go case by case and you tell me what I should have here in these 4 input, okay? So if I do the first one, that means if a0, a1 is 0, 0, I want to do x plus y. If I do the x plus y, what I should have in the second 4 inputs here? If I'm doing x plus y, just type on the chat box. If I'm doing x plus y, what I should have here? X plus y, definitely y, right? So this should be y0, y1, y2, y3, definitely right. If I do x plus 1, what I should have here in the second 4 inputs? If I do x plus 1, type it there. Yeah, 1, definitely 1. So maybe I could summarize that here for you. For if that's a 0, 0, actually use somehow as a draft here. If that's 0, this y should have in these 4 bits that I have. If that's 0, 0, you should have y, which is I should put y3, y2, y1, y0. If this is 0, 1, I do x plus 1, so that means you should give that y 0, 0, 0, 1. So how about 1, 0? If I have 1, 0, what number should goes to this second one? These four inputs that you have here for 4-bit adder. If you have these case x minus y. So whenever you want to do x minus y, what you usually do? You use the first complement, right? You actually say it should be x plus the first complement of the y. What's the first complement of the y? Is y3 prime, y2 prime, y1 prime, y0 prime, okay? So this is, if this happened, the input should be y3 prime, y2 prime, y1 prime, y0 prime. Why? Because we use the application of the first complement. We actually discuss that whenever you want to design a subtraction, okay? 4-bit subtractor. So tell me this, whenever this is the case, you have 1, 1 is A0 and 1, and you want to do x minus 1, what should be these 4 input here? You want to say -1. What we should give here? X minus 1 is what we should have here. Whenever that's 1, 1. So you say x minus 1 means x plus the first complement of the 1. What is the first complement of the 1, which is here? What is the first complement of the 1? The first complement of the 1 is 1, 1, 0, right? First complement of the 1, you just convert 1 to 0, 0 to 1. That's actually the first complement, okay? So that means this is a whole story. So that means depending on what you have on the address bar, you give it different numbers on these 4 inputs that you have. So is it right? I actually say, okay, so that means I have for each of these inputs, just consider these 1 column here. Consider 1 column, okay? Which is connected to these Y3. So depending on the address A0, A1, which is these 2 bit, the possibility is Y3, possibility is 0, possibility is Y3 prime, and 1. So that means you have 4 inputs. Depending on the address, one of that input should be connected to the output. So which unit we need to use to do that? Mux or demux? So if you back to what we learned in the mux, so this is exactly the case that you need to use the mux, right? You have 4 inputs. Depending on the address, you need to connect one of them to the output. So that means you need a mux. So that means here, I actually put 1 mux here for each of these 4. So this is for one of them. This is the second one. This is a third one. This is actually the 4th one. So this is mux, and it is 4 by 1, right? What should be the address bar of these 2? You tell me what we should connect to these address bar. So definitely, who tells which one should be connected? This is A0 and A1, right? So you need to connect A1 and A0 for all of them, okay? So A1, A0, and this is 1A1, A0, okay? So now important is how many inputs we have? 4, right? This is 4, this is 1, 2, 3, 4. This is 1, 2, 3, 4. This is 1, 2, 3, 4. Okay. So help me to finish this. So for the first one, which is, so see in the in 4-bit adder, this technically should be y0, right? This should be y1. So this should be y2, this should be y3. But depending on these address, it's doing a different work, so it should be use these max. So whenever that's 0, 0, let's see what we should have here. Whenever that's 0, 0, so it should be actually connected to, yeah, see, this is actually y3. So if you are talking about y0, you need to consider this column that we have. Okay, this is y0. Okay, so that means whenever this is 0, 0, y0 should be y0. Okay, what should be the next whenever it is 0, 0 should be y1. So that's the reason the all first of them should be connected to the y, right? So this is should be y2, this should be y3. Does it make sense? So whenever this is 0, 0, which input connected is the first one. So that means I have y0, I have 1, 1, 1, 2, y2, and y3. This is exactly what I want, right? Whenever that's 0, 0, I should have y3, y2, y1s. Okay? So how about next? For the 0, 1, which is 1, I should have 0, 0, 0, 1. So that means y0 should be 1, the rest should be 0. So that means I connect 1 to here, and all others should be 0. This is 0, this is 0. Okay? So help me in the next one. What should be the next here? You actually back here. It's connected to this whenever you have a 1, 0. It should be prime, right? The y0 prime, y1 prime, 1, 2 prime. Okay? So that means you should have, for the third one, you should have y0 prime. This should be 1, 1 prime. This should be y2 prime. And this should be y3 prime. Okay? And finally, the last one, whenever it is 1, 1, it should be just 1. y0 should be 0. The rest should be 1. So that means it should be connected to the 0. This should be 1. This should be 1. And this should be 1. Okay? So yeah, you see you have 1 y prime 0 for this, 1 y2 prime 0 y2 prime, and similar for the others. Okay, so just understand what we did. It is very simple, right? Based off these address, you need to actually give the specific things to these actually 4 bits that you have here. We actually put the max and use these fact. Whenever it is 0, 0, it should be x plus y. So that means the all y0, y1, y2, y0 connect to these 4. So whenever it is x plus 1, which is 0, 1, whenever a0, a1, 0 is 0, 1, you have connected the second pins of the max to these y0, y1, 2, right? So that should be 0, 0, 1, 0, 0, 0, 1. So that's what you have, 1, 0, 0, 1. And similar for the others, okay? So that means we figure out what we should have as a x, what we should have actually as a y here. So that means whenever you have a0, a1 based off this table, exactly we actually have the right value for y. So we are done with the y. But still we have some other actually figure out about what we should have for these 2 and also these 4. So back to here. So you tell me, this is the same topics that we had whenever we want to design the subtractor, right? So if you remember, whenever we want to design the 4-bit subtractor from 4-bit adder, which gate we add to the outputs? Remember that what we put in the outputs and why? Remember that we say, okay, we need put the XOR. Why we need to put the XOR? So see, this is S0, this is S1, this is S2, this is S3, and the second pin, the second input is, we call that C control. So let's see, you need to have the same thing here. Yeah, we say control. We will design that later. So remember why we did this? Could anyone tell me why we use the XOR on the output whenever we want to make a subtractor from 4-bit adder? Any idea? I actually use this part. So remember, I talk about the switch XOR. Remember, I put one X, I put another one C. Then you have these output, which we call that F, right? So definitely F is xc prime plus cx prime based off definition of the XOR. So based off that, if I give c equals 0 and c is 1, whenever c is 0, what should be the F? Type on the chat box. If c is 0, what should be F? So see, this is a simple thing. So C is 0. This is a definition of this. You put this C is 0. So this second term is 0. And the C prime will be 1, 1. And the X, you have X, right? So the F is X. How about C equal to 1? Whenever C equal 1, what should be the F? What should be the F? So again, back here, you say this time C is 1, prime is 0, you have 0, yeah, definitely should be X prime, okay? So I explain this whenever we design a subtractor, okay? So the reason that you use the XOR, because XOR, if you consider one of the inputs as a control pins, with that control pins, you could have another input, which is X, or you could have its prime, right? So that means whenever you want to have one output itself or its prime, definitely you need to put actually XOR here. Whenever you want to design the subtractor, you use this because, again, this is, I already explained this. Here I explain that again. Whenever you want to do X minus Y, we learn in chapter 1, we do X plus Y double prime. What is the X double prime? Is the first complement of the Y. Then we check the carry. If carry is 0, you take another complement, the first complement with the negative sign. That should be the answer of X minus 1. If C is the carry is 1, you just add that number by 1, right? So that means whenever you have the subtraction, the one case is you should prime the outputs if C is 0 or no change on the output. So that means these S will be prime or will be themselves. So that's the reason I put actually the XOR and I control this. If I need to have these S here with no change in the output of the XOR, the C should be 0. Okay. If I need to prime these inputs, I just give the 1 and I'm able to take a prime of them. That's the reason I put actually XOR. I explained that in the 4-bit subtractor. Okay. So that's the reason you put here. So now based off this, based off what we want to do, we want to design this, which is we should have one C4 and we need to have one sign. We need to design that. We need to design this. And also we need to know where I need to connect this C control, okay? So for doing that, we actually need to design a combinational circuit. So let I borrow something from other file. Just copy this and paste that somewhere here. Okay. Yeah, I put that here. Maybe expand that. Okay. So I don't know, it could be that. Yeah, we could do that. So right now I want to design these two, right? Actually, three things. The first question is what I need to connect to the C control that I put here. Question number two, where I need to connect these C4 and where I need to connect these sign, okay? So I actually say, okay, I need to design for function. So the first one is C4. I don't know what I should do with this C4. The next one is the sign. I have no clue what I need to do with this sign. And the last one, actually, let's do one thing. Let's just consider the first one. So let's do this. Let's make that smaller. Just for now, let's consider C4. I want to know where I need to connect these C4. That's a design problem. So we talk about how you could design combinational circuit. Right now, I want to design a C4. The question is, C4 is related to which variable? Okay, this is an important question. So you tell me this C4 that you have is related to which of these variables that we have here. Is it related to A0 and A1? This is the first question. Is A0 and A1 has the effect on the C4? Yes or no? Yes or no? So definitely answer is yes. Why? Because depending on the A0, it could be x plus 1, x minus 1. If you have x minus 1, definitely there is no C4, right? You have C4 whenever you add x plus y. So definitely no doubt the C4 function is related to the value of A0, A1, or I add here. So C4 is the function which is related to A0, A1. So what else we could say? Which other parameters affect these C4? So is it related to these? C4 that we have? That means this C4 that I have here. Maybe that's better to say. I don't know. Maybe the AU actually the AU C4 is label as a C prime 4. I call this C prime 4, which is the C4 for the AU. But I have the C4 for 4-bit adder, right? I call this C4, right? C4 are the 4-bit adders. C prime 4 is the C4 for the AU. So definitely C prime 4 should be related to the C4 that you have from 4-bit adder, right? In some cases, it is exactly the same thing, right? So I give the two different names. So that's the reason I add C4, okay? This function is related to the C4. What else actually it could be related? I put C4 here. We need actually one other. It's related to the one other variables. I add that variable here. So is a C4 related to the C in that we have? Is C in? The answer is yes. Why? Because if again check the 4-bit subtractor, whenever you say x minus 1, if this is the carry is 1, you need to add by 1. How you could add by 1? You connect this C4 that you have here to this C in that you have on your 4-bit adder, right? If you check the structure of the subtractor, we connect this C4 to C in. That's the reason it should be related to C this C in. So that's actually the truth table for this function, right? So you have one function, I call that C prime 4. It's related to A1, A0, C in, C4. I want to design that and see what's the combinational circuit for that that's able to do the same thing. So You say I have the 4 variables, I have 16 different bit pattern, you actually list that here. So then complete the truth table. So just consider whenever you have 0, 0, okay, 0, 0. Back here, whenever you have A1, 0, 0, it is adder. So you need to say x plus y plus c in. So that means what you should have here for C prime 4 whenever you just add these two numbers. So what it should be, whenever you actually added that two numbers, so Amin actually, let's see, should it be C in or not? So what we want to actually design here is not actually C. Yeah, this is actually what we let's do this. So here I need to make some changes here. I change these label, okay. Change this label to not this, probably also this one too. I just changed the label that make more sense, the name of them. So I actually call that C0 or is the C in for the 4-bit adder, okay? So yeah, the C in is whatever we have here, definitely. So I actually have the C in here. And probably I need to change the one other name because it somehow gives C4 and C prime 4 is a little confusing. Okay, I'm going to change these label. So I changed this name, not C prime 4. Actually change that to C out. Okay, C out. C out is the C4 for the AU, but the C4 is whatever you have for 4-bit adder, okay? So that means what I want to do, I want to design the C out, right? I actually changed that label to C out, okay? So just make sure what we did. For this scene, we call that C0, that's right. So then the next thing that we change is the C out, which is the whatever you have for this, and the sign is same. Okay. So if this is C0, I want to do this. I want to know what I should connect to this C0. Okay, so I want to design that C0. I say definitely what you connect here is related to A0, A1 because depending on that subtractor or adder. So if that's actually adder, it should be C in. If that's actually subtractor, you have nothing here, right? So definitely it's related to A0, A1. So it's actually related to C in. What is the C in? C in is whenever x plus y, you have the input carry, which is you add with these x and y. So that means whatever you have here definitely should be related to this C in, right? So what else is related? Is related to C4 because why? Because whenever you have the subtractor, if you check the subtractor circuit that we discussed before, it's connected to the C0. So for that reason, C0 is related to these 4 variables, which is I list this here. And because they are 4 variables, each one could be 0 and 1, you actually have 16 different cases. So we actually, over the class time, if you have any other classes, you could leave the class. I'm going to record that. I need to finish that today because if I don't finish, I need to spend too much time in our next class to finish this topic, okay? I actually keep going. Probably I need more 10 or 15 minutes. So it is fine if you have another class or you have to leave, you could leave. But continue until I finish this. Okay. So I want to design the C0. I want to know where I need to connect. I say, okay, this is a function I want to design. So it's related to the which variables. It's related to A0, A1, Cin, and C4. Okay. So that means I make one truth table. So you have 4 variables. You are actually have 16 different bit pattern. I list all 6 different bit pattern. So I back to each of them and complete this truth table. I start with the A0, 0 whenever they are 0 and 0. See, here to here, I just separate that. Maybe it's more easier to follow. So see, I'm talking about these 4 cases, which is the A0 and A1 is 0 and 0. Back to this table. So whenever they are 0, 0, this is what we need to do. X plus Y plus Cin. So that means what should comes to inside this C0 definitely should be the Cin should be connected to C0 that we have, right? So for that reason, I say in this 4th case, C0 should be the same with Cin. So what is Cin here is 0, 0 should be same. I put 0, 0, and here should be 1, 1. Okay. So that's what I complete for these 4 cases. Go and check the other 4. So see, whenever A0 and A1 is 0, 1, again, I back to this table and see what we should have whenever we have 0, 1. You should say x plus 1. So do I need to connect anything to this C0? The answer is no, because whenever you have x plus 1, you just add x plus 1 and you don't need to actually have any Cin or the carry in, right? So definitely in that case, you should just have the 0, right? So that means CO should be 0. I put just 4, 0 here, okay? So then I check the other 4 different case. So which is here, which is A1 is 1, A0 is 0. I back to this table. 1 and 0 should be x minus y. Remember, if you check the 4-bit subtractor, whenever you want to do x minus 1, if you check that circuit, what we connect here, we exactly connect C4. Okay, we connect C4 whenever you want to actually do the subtraction. So that means in this case, it should be exactly C4. C4 is this column. So that means whatever you have for C4, it should be exactly the same. This is C4. Here is 0, should be 0. Here is 1, it should be 1. Here is 0, should be 0. This is 1, and this should be, okay? So that's exactly is the same thing. So, and let's to check the last 4 cases, which is A1 and A0 is 1 and 1. So check these 1 and 1. Again, this is the subtraction. Whenever you have the subtraction, if you check the 4-bit subtraction all the time, we connect C4 to C0. So that means in this case, C0 should be C4. So this is a C4 column, and it should be exactly the same with C4. Here C4 is 0, this should be 0, this should be 1, this should be 0, this should be 1, okay? So, yeah. So that means you could actually get the circuit for that. Here you could say C0 equal to sigma midterm. Which midterms? You just check where it is actually is 1, right? The rest should be easy. So this is actually is 2, right? So this is 2, this is 3, right? I add here is 2, 3, where other place it is 1. So here is 0, 0, here is 1, which is, what is this? This is 8 plus 1, we have 9, right? We have 9, we don't have 10, we have here 11. 11, 12, 13, 14, and 15. We don't have. Okay? So you already know how you could simplify this, right? You need a K-map and get the simplest form of the 0. I'm not going to draw the K-map. You already know. You actually do that yourself. the simplest form that you got if you actually simplify that is this. So it should be equal to, if you make that simple, the C0 will be A1 prime, A0 prime, C in plus actually what else you have, A1 C4. This is what I got, but you need to do that. You need to actually make one K-map. You tell me the K-map should has how many squares. So you have this function is the function of the 4 variables. You need to make with 16 square and make this simple. We did that a lot in the K-map chapter, right? I don't want to actually waste our time here. You use the K-map and get the simplest form of this function, which is this. So that means right now I know what I need to connect to this C0. Okay, see what I'm doing here for C0. Definitely this is one OR in the middle, right? So I make one OR. This is actually the OR. So this is the OR. This is OR. So how many sentences we should have? 1 and 2, right? So that means this should be connected to 2 and. This is the first and. And what should be the, this is actually 1 for this, 1 for this, okay? So what you should connect to the first one, you need 3, right? So A1 prime, so should be A1 prime. This should be A0 prime. What we have is the C, okay? What should be the next sentence is actually A1 and the C4. I just implement these functions that I got with the gates and connect to C0, okay? So that means right now you understand why we have this circuit connected based on the design that we have here, okay? So similar to this, we need to actually figure out what we should have for this, where I need to connect these control pin, and also what we should have for this sign and C out and the sign for the AU. We need to do exactly the same thing. That means we should have one design problem. I'm doing that here. So let I actually borrow another truth table here and put that here. Yeah, maybe here we need to expand that. Okay. So what else actually here missing is I want to actually get the C out. I don't know what I should do with the C out that I have. The next is the sign. I have no clue what I need to do. The sign, I actually the control, which is control that XORs. I have no clue what I need to do. So the question is, okay, if you want to design these 3 as a output, so first you need to know what these 3 output is related to which variables. So the first question is these 3 related to A0 and A1? Definitely the answer is yes, right? Whatever you have here should be the function of A0, A1, because with the different A0, A1, you are doing the different job. No doubt you need the A0 and A1. So what else you need actually for these 3 function? Is they related to the C4? So the answer is yes. Whenever you actually have add or subtractor based off these concept that we learned in chapter 1, it's take a look to the carry, right? The carry is C4 here. If this is 0, it's positive. It is 1, is negative. So that means definitely sign is related to C4. So it should be fit there. How about C out? C out is the same with the C4 if you just have the adder. Definitely it should be related to the C4, okay? How about these control? What control this? 4 XOR, definitely these carry that you have, these C4 that you have. So that's the reason definitely these controls should be related to these 4, okay? So this time, because you have just 4 input, so each of them could be 0, 1. So definitely you have just 8 cases. So I summarize these 8 here. So then you need to complete these truth tables. So this is important, okay? So just again, take a look. What is the C out? C out actually is somehow the same C4 that we have. Just first let to complete this. So let's see, first, similar with the previous design problem, I actually consider these two first, because in this, these are should be add x plus y. Here should be say x plus 1. Here should be say x minus y, and here we should have x minus 1, right? It's exactly the same with this table that you see. 0, 0, x plus y, 0, 1, x plus 1, 1, 0, x minus 1, 1, 1, x minus 1, okay? So I just somehow consider these as 4 different cases. So here in these 2 row, it is 0, 0. A0 is 0, this is 0, this is 0, this is 0. That means you want to add x plus y. So whenever you have x plus y, what should be the C out? So the C out is exactly same with C4, right? So that means for these two, C4 should be C out. Why? Because the C4 actually technically is the same thing with the C out, right? Whenever you add the two numbers, the C4 is what we call the C out, right? So that means we just put 0 and 1. Same thing for 0, 1, because it's 2x plus 1. So again, it should be the same with the C4. So that means here you have 0, 1, okay? So how about these other case? Whenever this is 1, 0, you actually say x minus 1. Whenever these are 1, 1, you have x minus 1. For 1, 0, you have x minus y. So whenever you have the subtraction, which is these last 4 rows, definitely you don't need to C4, right? C4 is meaningless whenever you have the subtraction. So that means if I put C4 actually should be 0 for this 4 case, okay? So I complete that for CR. How about for sign? Help me. So this is a sign. Whenever you have these 4 cases, which is here to here, you do, for these two, you have x plus y. So whenever you have x plus y, what should be the sign? Consider 1 as a negative, 0 as a positive. So whenever you add the numbers, do you get the negative numbers? The answer is no, right? So that means whenever it is added, which is these 4 rows, definitely it should be 0, which is positive. So whenever you have the subtraction, which is these 4 case, so you need to actually take a look to the C4. If you have the carry based off these concept that I explained, whenever you have actually carry is 1, it is positive, you just add with the smallest 1. Whenever it is 0, you should get the negative number. So that means whenever carry is 0, which is here, you have the negative. Here is 1 is negative. So let's see, whenever it is 0, so that is wrong actually. Here should be just, so see where it is 0, here C4 is 0, should be 1, here is 0, should be 1. The rest should be actually 0. We have positive number, okay? So that's actually is for sign. How about the C control? The control. So back here, so when we should have the numbers without actually prime, the control is C0, no prime. Where we should have the no prime depend on C4, right? So if C0 is 0, you need to take a prime. That means C should be 1. Whenever C4 is 1, you don't need to get the prime. You should have the all S. So that means C0 should be 0. So just let to start first whenever we don't want to have the prime. So the C should be 0. If C control is 0, you don't need, you have the same numbers that you have here, right? So back here, so C, when you have actually the same numbers, whenever carry is 1. So that means whenever C4 is 1, right? So whenever C4 is 1, so let's actually consider like this. So again, I consider first 4 row, okay? So that means 1 to 4. You have 0, 0, 0, 0, 0, 1, 0, 1. So that means you have the adder. You are doing x plus y or x plus 1. So whenever you do that, so the s, whatever you have here, definitely should be here. You don't need to take actually the prime because that's not the subtractor. It has happened whenever you do the subtraction, right? So that means for these 4 case, you should have the same numbers that you have here. The control should be 0. So that means you have 4, 0 for whenever you use that as an adder, x plus y or x plus 1. So whenever you are in these 4 case, so that means 1, 0, 1, 0, or 1, 1, which is the subtraction. First 2 is x minus 1, the next one is x minus, first 2 is x minus 1, the next 2 is x minus 1. So you check the C4, right? You check the C4. If C4 is 0, you should take it to first complement with the negative number. So that means here you have 1, and again here you have 1. The others should be 0 and 0, okay? So as you could see, the C control is exactly the same with the sign, right? Sign and the control get exactly the same thing, but C out is different. So similar, now it is a design problem, right? You say C out is the function of A1, A0, C0. It is equal to sigma midterm. Which midterm? Help me. C out is 1. And what is else is 3. So 1 and 3, it is equal to this. So you have the, so then let's do the same thing for sign and the control. Sign equal control because they actually have the same truth table, right? Equal to sigma mid-10. Which mid-10 for sign and control? We have 1 to 4. You have 4. And this is 4, and what is this? This is 6, right? This is 6. 4 and 6, okay? So use the K-map to actually simplify the function, which I'm not going to do that, just I write the simplest form. So you do that yourself. If you do that, C out, I just write the simplest form after you use the K-map. The sign equal to control equal to, this is what I got. I got for actually for the sign and also for the control, I got A1 and C4 prime. This is for the sign and control. And for C out, I got actually this. I got C4. For C out, I got C4, and with A1 prime. Okay, you could check yourself. You just be careful. K-map should be has 8, actually 8 squared, right? Because this is the function with the 3 variables, right? 2 power 3 is 8. So if you use that, so C4 A1 prime I got for C out, and for the C sign and control I got A1 C4 prime. That's it. That's actually what I need. Then I just implement these 2 functions here and connect what I have. Okay. So see, I want to make the C out, so I say C out should be, I first put 1 and I call that cout. So I exactly implement whatever I got here, C4A1 prime, okay? So one should be C4, the other should be A1 prime, right? A1 prime, okay? So that means cout is C4A1 prime, and the next one, the sign and control is A1 C4 prime. So that means if you have these as a sign, because sign equal to C control, so I actually connect this to this because both is the same value. You need actually one and, which is, just check that again, sign and C control is A1 C4 prime. So it should be A1 and C4 prime. So you actually add one prime here. So A1 C4 prime is sign and also is the C control. Okay. So that means this is actually the example, which is somehow is a good example to use the all skills that you learned so far. So we design actually the arithmetic unit, which has two not address, actually two pins, which is tells which actually function these AU do. So whenever that is 0, 0, it's add these x plus y plus c that you get. Whenever that is 0, 1, it add these x by 1. Whenever it is 1, 0, it subtract these two. And whenever it is 1, 1, it subtract these x by 1. So what we did, we just use one 4-bit header. We connect x here. We use the mux because we have 4 different actually option whenever we have the different value for A0, 1. Okay, we use the mux 4 by 1 and connect these here. And for the sign and cout and the scene, we just actually design 4 combinational circuit. We figure out, okay, we need to sign. We consider that as a function and say it is related to the which variables, okay? So for sign, cout, and the control related to A0, A1, and C4, and C0 related to A1, A0, C, and C4. So we actually know what should have on the left side of the truth table, but we fill out these right side based on the function that we want to have. Same thing for here. You complete the table, then you implement that output with the Boolean function. You actually make that simple. You got the simplest form, then you implement that simplest form with the gates and connect to that actually the output pins that you want to have. Okay, so it is simple. If you actually review that yourself 1 times more. So what I recommend to do first, go and check the 4-bit subtractor. Okay, if you understand completely what we did in the 4-bit subtractor, so whenever you come back here and see what we did, it is actually very easy. Okay, so this is the, but if you don't know what we did in the 4-bit subtractor, it is actually some part of this shouldn't make any sense. But if you review how we design 4-bit subtractor, it should be very easy. Definitely you understand what we did actually here.